Often, when we write code, we have to wait on certain things that take time to happen. Things that take time are usually things like I/O, such as reading or writing to a disk, getting data from a database, downloading a file, and so on. Sometimes, things that take time could just be computationally expensive, such as processing large amounts of data. Usually, our programs are complex with multiple parts to them. For example, applications often have a user interface, whether that's via a terminal, a web page, or a full desktop GUI. If our application has to do things that take time, we don't want other aspects, like the UI, to freeze up, unable to do anything while we wait. Asynchronous programming is an implementation-independent way to structure our code so that we can continue to work while waiting on other things. This series is accompanied by a free book. Check the description for a link straight to this chapter. My name is Daniel. Welcome to Iris. Asynchronous programming doesn't necessarily mean threads. Some languages that support async programming don't even support multiple threads. Under the hood, we might use threads, or we may depend on operating system hooks, or even, for embedded programming, we might depend directly on hardware interrupts and exceptions. In this video, we're going to explore the modular design of async programming in Rust. Our aim is to get a solid-ish understanding of the concepts involved, even though in the real world, you're likely to depend on others to design and build the more complex parts of the system. Before we jump into the main part of the video, we once again need to talk about memory, specifically moving and pinning. All data in our running program exists somewhere in memory, whether it's the stack, the heap, or static memory. That means that everything has a pointer, an address in memory. When we pass a variable to another function, ownership of that variable moves to the other function. When we add a variable to a vec, then ownership of that variable moves to the heap. Anytime data moves ownership, it also physically moves in memory. We can see this in action with some simple code and some knowledge about pointers from our previous video. We'll create a string type and give it to the variable greet. As we know from last time, the data we care about, in this case hello world, will be stored on the heap. The variable greet contains some metadata about where our string data is on the heap, but greet is stored on the stack. We can get the pointer address of where greet lives on the stack like this. Now let's move greet to another function and get the new greet pointer. When we run the program, we get two similar but different addresses. This is usually fine, but occasionally things might need to know where they themselves are in memory. This is called self-referencing. If something references itself and we move it, where does that reference now point? Let's create a completely ridiculous struct that contains some data and a pointer to that data. When we create the struct, we'll need to set the pointer to none because the constructor itself will move the data. Instead, we'll set the pointer via a method after it's been moved into place. Finally, we'll do the really stupid thing and dereference the pointer into the value. Let's not forget that safety comment, that's better. Let's write some code to instantiate our example struct. And now that it's in place, we can set up that pointer. When we read the value via the pointer, it, perhaps surprisingly, works as expected. We can also change the value directly, and the pointer correctly gives us that updated value. Now let's move ownership, and yes, this is actually enough to do that. We're technically moving it within the same stack frame, but this is a new variable, even if it has the same name. Updating the value works, but reading from the pointer gives us the old value. Pointer to value is just a numeric address of a location in memory. We moved the data, but the pointer is still pointing at the old location. Self-referential data is dangerous, but it can also be useful in certain circumstances. Okay, not in the example I just gave, but still. For this reason, some generic types occasionally need to take it into consideration. To keep ourselves safe, we can pin arbitrary data to memory, preventing it from being moved. We use the pin type to express this behavior. Pin used to confuse me, but I actually don't think it's doing anything remotely clever. The type itself is just a container for a mutable reference, so the pin itself is safe to move. Through the magic of the borrow checker, holding that single mutable reference is enough to lock the data in place. It's more like a guard or guarantee than anything magical. We can pin our example from earlier using pin new. Although you can't always use this, it's kind of goofy and I'll explain it in a minute. We now can't modify the original struct or move it because pin is holding the mutable reference, but we can modify the data via the pin thanks to deref and deref mute. We can also move the pin, and unlike our earlier example, this works because the pin just holds the reference, our data doesn't move. There's a lot to pin, so if you're curious about it, the standard library documentation has a lot more information. For this video, it's enough to know that in specific circumstances, like in modular asynchronous architecture where we don't necessarily control everything, we need to be certain data won't move unexpectedly, and this is achieved through the pin type. Pin new only works with types that are unpin, which is the automatically implemented marker trait for types that don't need to be pinned. I told you it was goofy. For things that do need to be pinned, you can use things like box pin and the pin macro, which have their utility, but crucially, do move the data you're trying to prevent moving, so take care of your references. That said, you would have to box a pin if you wanted to return it. You couldn't pin it to a stack frame that's about to be removed. In our example, this is fine, so long as we set the pointer after moving it into the pin. When we build software, we can compartmentalize different parts of our program into tasks. Imagine we want to download two websites and compare the contents. We download website A, then we download website B, then compare the contents of the two sites. However, now that we've broken it down into tasks, we can see that the tasks for getting the websites don't depend on each other and could be performed at the same time. Asynchronous design allows us to reason about our code at the task level. It doesn't specifically tell us how that work will get done though. Different languages provide asynchronous utilities in different ways. In C#, the default way async tasks are run is using multiple threads in a thread pool. Node.js is a single-threaded runtime though, so async code uses operating system callbacks to let your program know when a task is complete. Importantly, in both languages, async code just works. You can start using it out of the box. Rust provides ways to structure asynchronous code, but doesn't have a default way of making sure asynchronous work is actually performed. Arguably, this makes async Rust harder to work with than other languages that support async fully out of the box. However, this allows software engineers to choose the method of task execution that will work best for their application. Over the rest of the video, we'll go over the Rust way of thinking about asynchronous tasks and create our own way of getting the work described by those tasks to run asynchronously. Asynchronous architectures allow us to break up work so that we can process different bits of that work while waiting on other bits. As discussed, conceptually, we break the work into tasks and then have some sort of scheduler that decides which task gets run and when. In Rust, we represent tasks with the future trait, which can be applied to any type. We manage task scheduling through what we usually call executors, although sometimes runtimes, which themselves use wakers to decide when to run different tasks. This sounds complicated, but by the end of this video, you'll hopefully have a reasonable idea of how futures, executors, and wakers work together, and if you don't, that's actually okay. Most of the time, you won't need to write any of these things yourself, but having even a vague understanding of them will help you write better async code, as well as spot and fix common issues you might run across. Let's start by building up our understanding step by step. The future trait represents a task that may or may not be complete, something that will be complete in the future, but not necessarily now. It has an associated type output and a single method poll. Output represents the type of data eventually returned by the future. Usually this type will actually be a result, because if we're waiting on something happening, there's a chance that it might not. The poll method is a lot more interesting though. Firstly, you'll notice that self is typed, which we haven't seen in this series before. In futures, self is a pinned mutable reference to the data of the type the future is applied to. The reason for this is that where the future executes might change. But because you might want to apply a future to self-referential data, we need to know that data won't move. Poll also takes a mutable reference to some sort of context type. For now, the only thing context contains is a waker, which we'll talk about later. The reason we don't pass the waker directly though is that in the future of futures, we might want to add more data to that context. Finally, the return type of the poll method is a poll enum. The poll method should be called anytime we want to make progress on a task. The return type tells us whether that call has resulted in an output, represented by poll ready of self output, or if the future is not currently complete and needs to be polled again, represented by poll pending. Once a future has returned ready, you shouldn't call it again. The official documentation explicitly says calling poll after ready may result in a panic. We will be breaking this rule later, but we'll be really cautious when we do. Let's make our first future then. We can apply the future trait to anything, even a unit struct is fine. For now, our poll method will immediately return poll ready with a static lifetime string slice reference. We'll instantiate our unit struct and immediately pin it. Next, we're going to create a context with a no-op waker. Now, don't worry about this yet. The no-op waker doesn't do anything, and we're not even using the context in this example. Unlike some languages, in Rust, futures don't do anything unless you call the poll method, so we'll do that and we'll store the response. We can then use a match to extract the output from the poll enum. Normally, futures won't be ready immediately and will need to be polled again. Let's create a future that doesn't complete the first time you poll it, using a simple counter. Each time the poll method is called, we'll check if we're at 0 by dereferencing the pin. If it's 0, then we're ready. If it's not 0, we need to change the work remaining. However, you'll notice that self is not mutable. This is where things get a little interesting. How you'll manage mutability in a future you write yourself might depend on whether the future needed to be pinned or not. If it did, you'll have to work out some kind of interior mutability mechanism for yourself. If it didn't, then in all likelihood your type automatically implemented unpin, which means you can safely take the mutable reference out of the pin with getMut. This consumes the pin, but lets you mutate the data via the mutable reference. So here we can subtract from work remaining and return poll pending. Once again, we'll create our future and pin it. Then we'll create another context that doesn't do anything. When we call the poll method, it consumes the pin, but we can get a mutable copy of the pin with asMut, so long as the pin is mutable. It's a bit weird, but easy enough to work with. Now we can poll the future until the work is done. So managing futures is just about repeatedly calling poll, right? Well, no, not quite. Let's create a simple executor that will just poll futures until they're ready. This executor takes a single generic future and loops over the poll method. Now, as I mentioned earlier, we can only use pin new if the thing we're pinning is unpin. We could restrict our executor to only accept futures that are also unpin, but using the pin macro will let us keep our generic interface simple and broad. Again, the pin macro will cause the future to move, but as long as no self-references have been formed yet, this should be fine. We'll create our no-op waker and context. Next, we'll repeatedly call poll on the future until we have an output, which we instantly return from the loop with a break, and from the executor via the loop. This is all we need, but for demonstrative purposes, let's add a bit of code to show how many times we called poll. We'll start the counter at 1 and add to it each time we get a poll pending to get an accurate number of times. We'll capture output here and return it at the end. Passing our previous example in, this seems to work quite well. We called poll 4 times, once for each of 3 fake works that we needed to do, and once to get that final poll ready. But futures usually wait on things like I/O or heavy compute tasks, which won't nicely finish after a set number of calls. Let's try mimicking that with a simple timer. We'll store a system time, after which our timer is considered to have ended, and we'll get that by instantiating the time with a duration and adding it to the current system time. When calling poll method for the future implementation, we'll simply compare the current system time to the time after which we want to end, and return ready or pending as appropriate. Let's give it to our loop executor and run it. Woof! 50 million calls to the poll method in 1 second. I guess this speaks to the speed of Rust, but wow, are we doing a lot of nothing real quick here. This work is going to take resources like compute time away from other tasks, so we really want to avoid this. Rather than us polling the future over and over, if only there were a way for the future to tell the executor when it should be polled again. Waker is a struct the future can use to inform the executor it's ready to have its poll method called again. Before we get to that though, we're going to update our program to use threads for both tasks and scheduling. It's important to note, however, that threads are not a necessary element of asynchronous Rust. There are other ways to achieve waking, but for simplicity of explanation, this is the approach we'll take. First, let's update our timer to use threads. This is a bit more complex, so we'll talk through each bit. This time, we'll capture the duration and save it for later. Once we start the thread, we'll store its join handler in here. We won't actually join the thread in the traditional sense, so to be honest, I'm not sure this is necessary. I just didn't like the idea of orphaning the thread. Next, we're finally going to use the waker. We need to store it and access it mutably from both the executor thread and the thread we're creating, so into an arc mutex it goes. When we instantiate the thread timer, we won't have a waker yet, so we'll use the no-op waker. This saves us using an option and is safe as we won't start the timer until the first poll, at which point we're given the real waker. Finally, to mitigate a potential race condition, we're going to mark the timer as complete, and again, this needs to be accessible from both threads, so this is also an arc mutex. To implement the future, first we need to access the future mutably multiple times. We know it's unpinned, so we're going to grab the mutable reference to the timer out of the pin with getMute. Next, we replace our waker every time poll is called. Normally, this will actually be the same waker each time, but it is technically possible to move a future from one executor to another, which might mean we need to use a different waker. Poll will be called multiple times, but if we haven't started the thread, we need to do that now. We can take a copy of the duration and clone the arcs for waker and is complete so they can be moved into the thread. The thread itself will simply sleep itself for the duration, then set is complete to true, then call the waker. Once the thread is set up and on each subsequent call of poll, we'll check if the timer is complete and return the appropriate poll variant. Some important notes here. First, I've used unwrap when getting the mutex lock primarily to make this code easier to read, but also because if either our inner or outer threads panic, the program's not recoverable for reasons other than locking the mutex. Ideally, you should at least use expect, or our future could return a result, but we'll come to that later. Second, thread sleep is not remotely accurate. It's guaranteed to sleep for at least as long as the duration, but might sleep for longer, unless you give it a duration of 0, in which case it might sleep, or it might not, depending on your system. Thirdly, there's one more thing in this code that I'm hoping if you already use a lot of async Rust, has you in cold sweats. Don't worry, it is safe, but we'll cover that at the end of the video. Before we move on, let's test our new timer in our old loop executor. Now when we run it, we hit poll 140 million times. Technically, I guess we start the timer a bit later after calling poll and constructing a thread, and also sleep's not that accurate, but also our comparisons are a bit cheaper. Still, this is out of hand. Time to fix it once and for all. First, we need a waker. The waker type itself is a concrete type, but when it's created, we can give it any type that implements the wake trait. To stop the executor from polling unnecessarily, our plan is to simply pause the whole thread the executor is on. This is called parking the thread. This makes our thread waker fairly straightforward. When we instantiate our waker, we can use the current thread function to take note of whatever thread it was created on. Now, when we implement the wake trait for it, all we do is unpark that thread. Parking and unparking is akin to pausing and unpausing threads. So, onto the executor. We've got the same signature as the loop executor, accepting any future and returning its output. We'll also pin the future before anything else, just like the loop executor. Our first real difference then is we now actually care about the waker. We can create a concrete waker from an arc of any type that implements the wake trait. By creating our thread waker on the same thread as the executor, that's the thread that gets saved for later. We'll then make our context from that waker. Again, all we need to do now is loop over the future. If it's ready, we'll break from the loop and return the value. If it's not ready, we'll park the thread. When our thread timer calls the waker, it unparks the thread, resuming the loop and causing the future to be polled again. Again, this is all that's needed, but to show the improvement we've made, let's add the counter back in. When we run our thread timer in our new block thread on executor, you can see that our code is much more efficient with our poll method only being called twice. Once to start the processing of the future and once more to complete the future after the waker is called. This means the program spends most of its 1-ish second runtime asleep, leaving resources like the CPU free to use. The whole point of asynchronous code architectures is that we break our code down into small tasks. Implementing our own futures is great for the very edge of our Rust code where we're waiting on some sort of I/O from outside our program, or something like a heavy compute task we control. Most of the time we won't necessarily even be doing that though, as there are lots of traits for dealing with common I/O tasks like reading files, accessing databases, or downloading files. Most of the time we just need to glue those bits together. This is where async await comes in. We can make any function or any block of code a future with the async keyword. When you write async in front of a code block, that block will be evaluated as a future, with an output type that matches that of the block. In this example, we simply instantiate and return a string, so the async code block is a future where the output type is a string. To use this future, we can pass it straight into our executor. When you write async in front of a function, then the return value of calling that function is a future with an output type that matches the return type of the function. This example also returns a string, but because the function is async, instead of getting a string when we call the function, we get a future where the output type is a string. In this case, we need to call the async function to get the future to pass to our executor. But async code blocks and functions do something a little bit special. They can work up to another future and then pause until that future is ready by using the await postfix. What's rather brilliant in async code though is that when woked. Anyway, the code resumes from where it got to. Furthermore, because we're waiting for that poll ready value, await will automatically unwrap it for you. Because our timers don't return any values, let's stack some async blocks. When we run this code, we go into future that uses that value, then into future with value, then into thread timer. The waker from that executor is passed all the way into that future, and then the executor pauses until it's told work can proceed. After we exit out of future with value, we get the value. More importantly, because the value is considered to be instantly available after awaiting it, and because most of the time when waiting on something we have to assume that thing might fail, we arrive at the most sublime pairing of Rust syntax. .await ? Functions that can fail should return a result. Futures always return the poll enum, but future output will regularly be a result. Let's create a future that could fail. This future will return the time since the Linux epoch in seconds, but only if that time is divisible by 2, otherwise we'll return an error. Then we'll call that function from another async function, and here is the magic. .await gets the poll ready value, which is a result, and the question mark operator either unwraps the OK variant or bubbles the error variant. We'll handle our error outside our async code. A successful run looks like this, and an unsuccessful one looks like this. This doesn't need to be the end of the chain either. Imagine a future that returns a poll of a result of a vector. You could .await, question mark, into iter, map, filter, fold, etc. This is another one of those Rust features that I think makes the language really nice to use. Anyway, because the await postfix works on any future and async code will resume from where it left off, we can await several futures one after the other. Await essentially pauses the execution of the code until the thread timer future is ready, then continues on from that point. So this code is amazing, right? Right? No, this code is bad actually, but the reason may not be immediately obvious. Let's time how long this takes using instant. The total time taken to run the timers is 3 seconds, which makes sense, right? We have a 2-second timer and a 1-second timer. Combined, that's 3 seconds. But that's the problem. The two timers in the previous example are stand-ins for some arbitrary work and are completely independent of each other. We should not be waiting for the first timer to complete before working on the second timer. That defeats the benefits of asynchronous programming. What would be more useful is if we do both bits of work at the same time. To do that, we need both futures to be polled, at least initially, together. This is often called joining. Here's a rough example of what a join might look like. I'm not going to go too deep into this code because most of the time you'll end up using someone else's join code. Even the standard library has a proposal for a join macro. If you really want to see all the code, it's in the Iris book. To gloss over it a little bit, the collapsible future is a wrapper feature that I made that takes any other future and stores the output after it's ready, so that it doesn't matter how many times you call poll. You'll see why in a moment. When we create a new join, we pass in 2 futures of any type, then we pass those to new collapsible futures. If you need to join 3 futures, make one of those 2 another join, or use someone else's better code. Let's implement future for join. For a join with the generic types f1 and f2, our output will be a tuple of f1 output and f2 output. When you poll join, it polls both inner futures, every time. This might mean we call poll after a future is ready, which is why I made the collapsible future type. Once both polls report ready, then we extract the actual output from the collapsible futures and return ready from the join. Using the join future, we can rewrite our example, passing the timer futures into the join and awaiting that instead. Now our program only takes 2 seconds because our 2-second timer doesn't unnecessarily block the unrelated 1-second timer from running. Ideally, you won't be writing inefficient joins like this one yourself. Most async crates provide their own version of join, such as Tokio's join macro and Smol's zip function. Even the Rust standard library has stud future join, which they're trying to stabilize. Rust doesn't come with its own executors or much in the way of future utilities other than what we've covered here. This is because the implementation details can vary significantly depending on what you're doing. For example, while here we've used threads, threads aren't necessary, aren't always available, and aren't particularly efficient in some situations. If you're working on an embedded microcontroller, for example, rather than parking and unparking threads, you might be better off using interrupts and exceptions to wake futures. If you're running code inside an operating system, depending on what you're doing, it might be more efficient to wait on callbacks from the OS to know when to wake a given future. Rather than writing your own executors though, you'll find that other people have provided executors for common use cases, such as those in the Tokio and Smol crates. These crates also come with a lot of utility types, functions, and macros, including substantially more efficient and ergonomic ways to join futures. They also usually have code for common features such as working with the file system or network traffic asynchronously, either via libraries or optional crate features. Beyond this, there are also executor-agnostic libraries which provide features for more specific needs, like Request, which provides HTTP-specific features, or SQLX, 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 which provides connectivity to a variety of different database flavors. So most of the time when you work with async Rust in the real world, you won't need to write executors and you won't need to implement the feature trait yourself. You'll use third-party libraries for features at the outer bounds of your software, join features with third-party utilities, and you'll glue it all together with features created with async blocks and functions. Returning to our rather silly example from the very beginning of this video, your async code is less likely to look like what we've seen so far, and much more likely to look like this. Isn't it beautiful? Sure, it's simplistic, but there's not a feature trait or pin in sight, and that's genuinely what async Rust programming is like in the real world 99% of the time. So why did I just try to explain all of this? Well, my hope is that when you understand what's happening under the hood, it'll help you make the best use of async and avoid, other than forgetting that you can and should pull as many features together as possible, there are two fairly common gotchas in async code. Luckily, they're much easier to spot when you have a fair understanding of what's going on underneath. The first is blocking. We use threads in our examples, but you may not end up using a threaded executor, and even when you do, some executors allow multiple features to run on a single thread. This means using any blocking code could prevent a thread from continuing until it's completed, which could impact the execution of some or all of your features. This is an easier mistake to make than you might think. For example, reading a file or TCP stream using the standard library will block your thread until the action is completed. Worse still is mutex, which will block a thread until the lock becomes available. If there are two features on the same thread and one has a mutex guard when the other requests a lock, the second feature will block the thread, preventing the first feature from dropping the mutex guard. This causes a bug called deadlock. If you cleverly notice that I used standard library mutexes earlier, good catch. Luckily, the specific way they're being used is safe. The locks are guaranteed to be on different threads. Libraries like Tokio and Smol either come with or provide separately their own interpretations of typically blocking behaviors that use features instead. The second gotcha is with borrowing and ownership. As we've seen, there's complexity around features that requires pinning to be a thing. This is because a feature might be moved by its executor, and if it is, self-referential data would point at old or even worse, freed memory. But it can get even more complex than that. Rust's ownership model means that the lifetime of a reference must be trackable to make sure it doesn't outlive its own data. This gets even more challenging with futures as the compiler needs to track references through deferred work. Thinking even more carefully about own data references and the memory and CPU trade-offs of cloning data can make async code harder to reason about. It's worth remembering that particularly for smaller projects, you don't have to use async, especially if it's causing your code to be more complicated than it would otherwise be. Hopefully, after this video, you have a bit more of an understanding about what's going on when you use async in Rust. There are a variety of crates that provide utilities for async Rust. Each crate does this their own way, so before you choose executor crates and future supporting libraries, it's worth reading crate documentation to understand the options available and the choices made. This is the end of Idiomatic Rust in simple steps. While there are many more language features available to you, I hope I've left you in a strong place to continue your journey. I think I want to do a follow-up video for Iris covering what you should do next on your learning journey, but after that, I think we're done with the series. I have some ideas of where to take Fio's quest, including some quick potentially language agnostic videos on software engineering patterns, but what do you think? What would you like to see from the channel next? Leave a comment or join our Discord. If you've enjoyed the series, remember to like and subscribe. My name is Daniel, and this has been Iris.